The process and instrumentation diagram is a very important diagram in which you'll find a lot of information that is important to you as a control engineer. Sometimes instead of the name process you'll find piping, and instead of diagram you'll find drawing. Well, this is a definition of the P&ID that I have drawn from Wikipedia. The P&ID is a diagram which shows the interconnection of process equipment and the instrumentation used to control the process. In the process industry, a standard set of symbols, and we'll talk about that later, is used to prepare drawings of processes. The instrument symbols used in these drawings are generally based on the ISA standard S5.1. ISA stands for International Society of Automation. The P&IDs are used for laying out a process control installation, so they are very important in the design phase. They play a significant role in the maintenance and modification management of the process, but also of the controller structure that it describes. And the P&IDs form the basis of the live mimic diagrams displayed on graphical user interfaces of large industrial control systems, and we have just seen this on the SCADA system WinCC in the example of the preheater. Here SCADA stands for Supervisory Control and Data Acquisition. It goes without saying that these P&IDs should always be kept up to date. Here is a list of items that you can find in a P&ID. You'll have information about the instrumentation, so the sensor, the type of transducer, the type of analog electrical signal, mechanical equipment with names and numbers, all valves with their identifications, process piping, sizes and identification, flow directions of material, and of course very important for us control engineers, the control structure. So the control inputs, outputs, interlocks, feed forward, cascades and things like that. Well, you should use the correct ISA identification and reference designations. Typically for measurements within a process, the first letter relates to the type of measurement, so F for flow, L for level, P for pressure, and so on. The subsequent letters will have to do with the type of device. Is it the controller, a control valve, and so on. So here you have a few examples. FC stands for flow controller, FT for flow transmitter, FCV for flow control valve. You should use the correct ISA symbols for the equipment. So here are a few examples. This is the symbol for a control valve, a manual valve, and so on. So please refer to the ISA standard S5.1, and there is also software available with libraries that will make it easy for you to select the correct equipment symbols and to draw nice P&ID diagrams. Well, here's an example that comes from the water level control of a steam boiler. You can see here that there are parts of the control structure, and here there are two measurements. You can see here that this is really a PT stands for pressure transmitter, so this is a pressure measurement, and over here you see here LT, so this is a level measurement. You will see that the representations of a P&ID controller in a P&ID and in this course are often simplified. So this is the P&ID controller as you know it, represented as you know it. So here it's acting on a pulper. So it's based on, so the PV is a level measurement, as you can see, because you have a measurement coming from a level transmitter. Inside the controller, the control error is constructed, so the level set point minus the level measurement, right? And based on this error, an output of the controller is constructed, the manipulated value that will be used to control the opening of the control valve. We'll come back to this particular process a little bit later. What we'll often do is simplify this representation as follows. Very often this will be the representation that we will use, and this means that we're using a level measurement to control the system using this control valve. So behind this simplified representation, you have to kind of imagine the level transmitter, the level set point, and the actual P&ID controller. Before talking about the paper machine example, I will show you a short video about the paper process. Well, the video that you're about to see is based on the references that you see here on the screen. The different parts described in the video, the pulper, the wire section, etc., well, they come from different machines. Very often also old technology is shown, for instance at the wire section, but showing old technology has the advantage that it's easier to see things and easier to explain things.
Fiber products come partly from the items in your recycling bin, but also from schools, office buildings, printing shops, and other industries. This is what we call the urban forest. Everything you put in your recycling bin ends up at the sorting plant. Paper and cardboard is compressed and tied into bundles to make them easier to transport.
The delicate paper web is now carried into the press section by continuously looped wet felts, which carry away most of the water and stop the sheet from tearing. The longer section of the paper machine contains the drying cylinders. These huge heated rollers dry the paper, giving it the strength to become self-supporting, ready for the processes which will determine its surface qualities.
We will now go over the different control loops in the paper machine example. You will see that controlling the paper process requires quite a bit of classical process control know-how, and we'll be able to make links with almost all of the control structures and controllers covered in this course. We assume here that the paper process is based on recovered paper bales. The paper bales are brought inside the pulper using a transporter or conveyor belt. in the pulper. The paper is shredded into pieces, as you've seen in the video. Water is added and the paper dissolves and the pulp, sometimes called stock, is formed. The main parameter or measurement that is associated with pulp is consistency. Consistency is the ratio of dry fiber content weight over total weight expressed in percent. This consistency tells you how thick the pulp is and how much fibers it contains. Let us have a look at the level control that you see here in blue. The level of the controller is adjusted using the control valve, which itself is used to adapt the water flow inside the pulper. Here it is very important to meet the level set point as close as possible. The process from control valve to level is an integrating process, and we'll see that a PI controller needs to be used over here. This is covered in section 6 about level control. So the consistency control loop is shown in red. The consistency of the pulp is measured using this transmitter and controlled by adapting the speed of the conveyor belt. In some cases, the speed of this conveyor belt is fixed and the conveyor belt is either running on or it is not running, and then you're in the off state. And what the controller should provide is the on-off sequence to the conveyor belt. This type of control will require PWM, pulse width modulation. This should ring a bell because this is a concept that you have seen in other courses, and this type of control is covered in section 6 on digital MVs. The pulp then leaves the pulper to go through centrifugal cleaners, also called cyclones. The heavy parts are removed from the stock. The pulp also goes through several stages of filtering and screening, but this is not shown here on the picture. What is important to understand is that these centrifugal cleaners, those cyclones, will operate at their best when the stock flow is not changing too abruptly. So what has to be avoided is, well, step-like flow changes through the cyclones. Well, we arrive now at the next control loop, shown in orange over here, and this is the level control in this tank. The level is controlled using this pump. This level controller will be quite different to the level controllers that we have seen over here. Here the level has to be maintained on set point in a very strict way. So what we'll see here at the output of this tank is that when a machine starts, for instance, there is a sudden step-like demand of pulp flow. So the output will look like this. So now imagine that you have a controller implemented here that is of the type implemented over here. So a controller that will maintain the level in the tank very strictly. Well, this step-like demand at the output will propagate to a step-like demand at the input. Okay, but remember that your cyclones will operate best when you do not have any sudden flow changes. Okay, so this is not something that we desire. We would like to see something that is smoothed over a longer period, something like this, right? So that this change is propagated over a longer period and you do not have this sudden stock flow changes through the cleaning stages. One way to achieve this is to use this tank here as a buffer tank. So the idea is that you allow the level to deviate from the level set point for a little while. So this can be achieved by implementing a so-called non-linear PI controller, and this will be tackled in section 6 again on level control. The pulp or stock is then pumped from the buffer tank to the headbox. The purpose of this headbox is to deliver the pulp through a lip so that a stock flow jet is formed that falls onto the screen, onto the wire section. There the paper web is formed, and as you've seen in the video, well, the water is removed first by gravitation and then subsequently by vacuum using suction boxes. At the end of the wire section, the paper web enters the press section, where the water content in the paper web is further decreased by pressing the paper in between two felts. Well, next the paper web enters the dryer or dry section, and the paper runs on steam heated cylinders to evaporate the remaining moisture content. The temperature of the cylinders is controlled using the steam pressure. At the exit of the dry section, the web is scanned and the relevant quality parameters are obtained: grammage in gram per square meter and moisture content in percent. Subsequently, the paper is winded on a reel. The grammage of the paper web is controlled by adapting the stock flow, as you can see over here. Now the distance between the headbox, and this is where you're influencing the grammage, and the place where you're measuring grammage, so that's at the scanner, well, this distance is approximately, let's say, 500 meters. Okay, so there is a huge dead time with respect to the main time constants of the process. This calls for specialized control methods. One option is to use a Smith predictor, and this is covered in section 6, or you can use also an internal model controller, and this is covered in section 7. In this type of control, well, usually an internal model controller is used. Depending on the grammage of the paper web, the speed of the production line needs to be adapted. A high grammage will result in a lower speed. This makes sense. The paper web has to spend more time when it's heavier in the dry section, as there is more moisture to evaporate. Now, if the production speed changes, this means that the delay, we'll call it dt over here, will change, because it is this distance that has to be covered divided by the speed. So you'll have units meters divided by meters per second, and you'll have something in seconds. So if the production speed is changing, the dead time is changing. You can see that the process dynamics will change with the operating point. In this case, the operating point is dictated by the production speed. If the process dynamics changes, this means that, well, the controller, the internal model controller, should change as well. And this is achieved by doing scheduling. And this is covered in section 6. The grammage control is affected by the speed of the production line and the consistency of the stock. An increase of the production line will require a higher stock flow, and an increase in the consistency of the stock will require a lower or a decrease in the stock flow. When the stock is thicker, it contains more fibers, well, you require less stock flow to obtain the same grammage. Let us consider a stock consistency change. You can do two things. The first thing that you could do is wait until the effect of the consistency change has produced a change in the grammage, and then your controller will react. This is the reactive way, and it will be slow. What you could do instead is, well, act immediately as soon as you sense the consistency change and adapt the stock flow accordingly. And this is the proactive way. If you do things correctly, well, you might even not see a change in the grammage. Well, here, since the two disturbances, well, consistency of the stock and speed are available for measurement, they can be used for feed forward, right? And this is covered in section 4. In this drawing, it looks as if, well, the internal model controller is directly interacting with the pump. In reality, here you have a flow transmitter, and you have also a local stock flow control loop. Okay, so what is happening is that you have an internal model control. This is the master. It sets the stock flow set point, and this local loop is implementing this, well, stock flow control. The advantage is that when there is a pressure drop in this line over here, this pressure drop will of course affect the stock flow, and this will be immediately picked up by this flow transmitter, and this local stock flow loop will reject this, well, load disturbance. This is a cascade, and cascade control is covered in section 4. The moisture content of the paper web is influenced by both the production line speed and the steam pressure in the cylinders. Well, depending on the grammage that is produced, the strategy will be different. For low grammages, the limiting factor is the production speed. So the production will be at maximum speed, and the moisture content will be controlled by adapting the steam pressure of the cylinder, and this is what is shown over here. Now for high grammages, the limiting factor will be the drying capacity of the production line. So the production will be done at maximum drying capacity, so you set all steam pressures at their maximum value, and you control moisture using speed as shown here on the screen. Well, in this paper process there are also coupling effects between moisture and grammage. For instance, if you control moisture using speed, this is when the drying capacity is limited, as we have seen. Well, you can see that the grammage is also influenced by this speed change. But in this case, since we have implemented a feed forward, well, this coupling effect will be mitigated by this feed forward. When the grammage is adapted using a change in stock flow as shown over here, well, this stock flow change has also an influence on the moisture content, so there is kind of an interaction, a coupling effect, and these coupling effects are not desired because they could cause the grammage and moisture controller to fight each other. We need decoupling, and this is discussed in section 6. As you have seen in the video, the dryer section is covered by a hood to minimize energy losses. Well, the airflow through the hood, as you can see over here, has to be controlled, and the airflow set point is really critical. If you play it safe and you set this airflow set point too high, of course you will have too much energy losses. If you set it too low, the so-called dew point, point rosé in French, can be reached in the hood, and the water vapor will condense in small droplets, causing paper breaks. The idea is to control as close as possible to the dew point without reaching it. Process control can be represented as a hierarchy. Level 1 corresponds to base layer control. This level is also sometimes called the field level. These are the devices, sensors, actuators, proximity switches, on-off valves, and so on that you can see in the field. The control that is associated is typically sequential in nature. Level 2 is the safety level. It involves environment and equipment protection. Safety instrumented control systems, so for example safety PLCs, that are physically separated from the general purpose control system, monitor the system and intervene when dangerous situations arise. Level 3 is the level that will be considered in this course. It involves process control for single loop systems and multivariable systems. The control will often be a P&ID control or a model-based controller, a simple model-based controller such as an internal model controller. The controller is often associated with a control structure that will involve, for instance, feed-forward cascade control and so on. Level 4 implements more advanced types of control that involve real-time optimization. One such method is model predictive control, and students in control engineering have encountered this technique in the course of my colleague Thomas Muser. The next level is the planning level. This level uses a computer-based management system called Manufacturing Execution System, or MES. This system monitors the plant from raw materials to finished goods so that management can plan, schedule the production. On top of this, you might sometimes find a management level which uses an enterprise resource planning system, or ERP system, for operational management at enterprise level. The control hierarchy is often represented as a pyramid, as you can see over here, and from bottom to top you will see that time scales evolve from a second or less at the field level to several days or months at the top planning and scheduling level. Similarly, you will see that the spatial scale will evolve from something that is very local, so for instance a unit part in the field level, to a production or even several production lines in the planning and scheduling level 5. In process control, the choice of the set point is very important. Let us take the example of the choice of the set point for the airflow that goes through the hood. If it is not chosen properly, this could lead to condensation in the hood, and this will of course cause economical loss. Variations around the set point and the speed at which PV goes to set point when you do a change of set point are very important. As I said, to prevent economical loss. For instance, if you're producing an 80 gram per square meter paper and you want to produce now 100 gram per square meter paper, this transition from one set point, from one product to another, should be as short as possible, because the product that is in between these 80 grams per square meters and 100 grams per square meter cannot be sold, so it corresponds to economical loss. Going to the set point as fast as possible is therefore very important. Variations around the set point must also be kept under control for security reasons, safety reasons. Think of pressure in a boiler or the level in a tank. Keeping the process value PV around the set point SP will also maintain the process around a working point, and this might minimize the effects of non-linearities. Another reason to minimize the variations around the set point is that when you decrease the variance around the set point, well, you can actually very often shift the set point itself. This is the very well-known paradigm: decrease the variance and shift the mean. This will be explored in the next slide. While minimizing the variations of PV around the set point, you should always look at the cost, and the cost is of course in terms of the control energy. This means that you should look at, well, set point PV, but also look at the manipulated value. This is sometimes forgotten, and this is sometimes even forgotten in control reference books. There are of course quite a few challenges associated with process control. Some PVs are not available for measurement because of the cost of the sensor, or because technology does not offer a sensing solution. Sometimes soft sensors, for instance observer-based sensors, can offer a solution, and this should ring a bell for control engineering students, as we have tackled this in the course of state space control. Sometimes the signals are noisy, so filtering offers a solution, or sometimes the sensors are badly located, so they will produce a dead time. So you should always look at the location of the sensors during the process design phase. Sometimes there will be several influences on the PV that you want to control, so you'll have to choose the correct influence, so the appropriate MV, and you'll have to mitigate the effects of the other influences using decoupling and or feed forward. Sometimes the control problem becomes challenging because of the involved open loop dynamics, so you have to tackle difficult dynamics. First example is if this is a step at the input in open loop and you have a large dead time with a small time constant, well, this ratio here, dead time over time constant, will make the problem challenging if this dead time becomes large with respect to the time constant. And of course, if you have an inverse response, this is something that looks like this, well, this will of course make things even worse. And inverse responses are linked to the zeros that are to the right of the imaginary axis in the Laplace domain. Sometimes the process is difficult to understand, and one reason for that could be that the process is simply non-linear. This will result in different dynamics around different operating points. We have already seen an example of that in the paper process. Well, the relation, the dynamics that goes from stock flow to grammage changes according to the operating point. The operating point is dictated by the speed of the line. We had seen that the delay in the system was operating point dependent. Well, let us now look at this paradigm: decrease the variance, shift the mean. This paradigm is often used to improve the economics of the process, and it's one of the important topics of this course. Most production processes have tolerances on PV, the process variable. It might be a lower tolerance or an upper tolerance. Here in this case it's an upper tolerance, and we'll call it tolerance plus. Let us take an example again in the paper industry. The paper producer is selling his paper reels to an end customer, and the end customer will say, well, the upper limit on the moisture content is 8%. If you go above that upper tolerance, you can take your paper reels back, and this is then economical loss for the paper producer. So the paper producer has to make sure that PV stays below the upper tolerance, and he can do that by selecting the set point in his moisture control problem. So how will he do that? He will look at PV, previous PVs coming from the past, and he will look at the 3 sigma value, and he will set its set point as follows. It will be the upper tolerance, so tol plus, minus 3 times the sigma on PV. He has had a course on statistics in the past, and he knows that in 99% of the cases the PV will remain below the upper tolerances if the production process is turning in a normal fashion. Well, as this animation shows, if the paper producer manages through control, through better disturbance rejection, to decrease the variance of PV around the set point, he will be able to shift the set point so that it becomes closer to the upper tolerance. Well, you can clearly see that the variations around the set point are clearly smaller in this second situation. This means that the standard deviation has been decreased through control, and this means that the associated set point that can be chosen, remember that it is the upper tolerance minus 3 times sigma 2, is now much higher. The application of this paradigm has allowed us to decrease the variance or the standard deviation of the moisture content, and this has allowed us to shift the moisture content set point. In this case, well, we have been increasing it. Well, assume that you control the moisture content using the speed of the production line. Since you have a higher moisture content set point, well, you can go through the dryer section faster, and this will lead to a production increase, right? Assume that you're controlling the moisture content using the steam pressure. Well, a higher moisture content set point will lead to lower steam pressure set points. So in terms of energy savings, this is clearly also an advantage. So you can see here that using this paradigm can be used to improve the economics of the process. And well, decreasing the variance is a really disturbance rejection. So disturbance rejection is really an important component of control. People have often the tendency to think that set point tracking is very important and forget about disturbance rejection. You can also see this in terms of the frequency or probability distribution. This line corresponds to PV average. If your controller ensures a zero steady state error, this will correspond to the set point. So by ensuring that this point here, set point plus 3 times sigma on PV, corresponds to the upper tolerance, well, you make sure that the probability that the actual PV will be in the interval set point plus 3 times standard deviation on PV and set point minus 3 times sigma on PV is approximately 0.997. So you have a probability that is very near to 100% that your actual PV will stay below the upper tolerance. And by decreasing the standard deviation, well, you can increase the set point, you can shift the mean. In summary, once the disturbance rejection has improved so that the variance or the standard deviation has increased, the controller set point can be adapted, the mean can be shifted to improve the economics. Depending on the control problem, the set point is either increased or decreased. In the moisture control problem, the moisture set point could be increased, and this led to an increase in production if moisture was controlled using line speed, the production line speed. Notice also that there is more water content in the end product, and often these paper reels are sold by the weight, so this is another advantage. Well, let us take an example where the set point is decreased, and such an example comes from the production of beverage packing material. So what you have is, well, board, right? So this is board, carton in French. And what is done is that a layer of polyethylene is extruded on this board, and then there is a layer of aluminium, right? And what happens is that the end customer that buys this beverage packaging material imposes a lower tolerance on this polyethylene layer, and again it's expressed, for instance, in grams per square meter, right? So the one that is producing this beverage packaging material will choose the set point as follows. He will say, well, I'll take the minimum tolerance and I'll add now 3 times the standard deviation that I see on my measurement of PE. So if the producer, through a better disturbance rejection, can decrease sigma, you can see that the set point here using this formula will be decreased. Well, this method is sometimes called set point optimization, and the idea is to keep the set point as close as possible to the upper or lower tolerances depending on the type of control problem. And in the computation over here, well, either you have an upper or a lower tolerance with the associated sign, and X here is the confidence level. In the previous example we had X is equal to 3, so the associated probabilities were 99.7%. In the previous example, sigma, the standard deviation, was computed by considering previous data sets of PV. You compute the standard deviation and then you obtain the set point, so that the set point was fixed. But you can actually monitor the standard deviation in a continuous fashion. Okay, what you could do is, for instance, compute a moving standard deviation over a fixed number of samples, and what will happen is that sigma will change so that you can continuously adapt the set point. Of course, if you do such a thing, well, you have to implement measures so that this computation of the optimal set point can be done in a safe fashion. For instance, that there is a maximum and minimum value, and that there is some gradient that is imposed. There are of course a number of benefits when you compare process control in automatic mode to manual control. The speed and frequency of action is better. So at every sampling instant you have a new MV that is computed, so the variations in NV will be smaller, and also the deviations from set point will be smaller. Well, the control action is based on a P&ID algorithm, so that you take quantitative decisions and they will always be the same under the same circumstances. Of course, you can run several controllers in your PLC so that you can do simultaneous variable changes, whereas an operator is of course limited in the number of controllers or processes that he can monitor. The consequences of process control in automatic mode is that the operator becomes a supervisor and that the productivity will improve and go together with more consistent product quality properties. Well, there is also a big chance that there is a reduction in the energy consumption and an increase in the operation safety. And since when you do process control, you have to do it on the basis of a model very often, you'll improve your understanding of the process. You might wonder why we are comparing process control in automatic mode with process control in manual mode. Well, even in a modern control system, manual mode might be encountered often. Manual mode, except in certain situations such as production startup, is often indicative of a problematic situation. For example, a control that is not tuned properly, a control structure that is not adequate. And what happens is that the operator does not have confidence in the control action and takes the controller to manual mode. These are the desirable features for regulatory control. Well, the first feature is not desirable, it is necessary. We have to impose the stability of the closed loop system. The second feature has to do with tracking. We want PV to go to its set point as fast as possible. So when there is a closed loop set point change, well, you have indices like settling time, rise time, and so on. Of course, you have to have an adequate disturbance rejection, and this you can see in terms of variation around the set point. You have to be insensitive to model and measurement noise. So this means that if the process, for instance, changes a bit, well, the process controller should still be able to control the system with adequate performance. And this is sometimes called robustness. It is, of course, important to meet these indices without having an excessive controller action MV. And well, it is important, if the process is non-linear, that you meet these performance indices over a wide range of operating conditions. In practice, it is in most cases impossible to satisfy all 6 features, so you have to look for a trade-off. Well, besides stabilizing the system, well, process control can achieve quite a lot of things. You can keep the process at the prescribed target. This is set point tracking. You can simplify transitions from one operating point to another. You can reject perturbations, so input load disturbances or output disturbances. You can robustify the system. You can make sure that your controller finds the optimum operating point. You can enhance process analysis and improve your process know-how. You can improve safety, security, extend the life of your equipment, improve process operability, and improve economics. Modern day digital control systems can handle thousands of variables in an accurate fashion. Everything happens in a decentralized way, in the sense that the analog to digital conversion is done locally, and then the information is communicated to the central PLC using a bus system. These systems have signal conditioning capabilities, so for instance noise removal and filtering, but also calibration possibilities of the different measurements. You can easily interact with the system using the HMI or Supervisory Control and Data Acquisition System, SCADA system. In the case of Siemens, well, it is the Windows Control System, WinCC. You can interact with the system through faceplates for motors, valves, controllers, and the alarms pop up and they make it easy for you to locate the problem or the interlock. The alarms come with occurrence statistics so that you can do a Pareto analysis, if you tackle 20% of the most frequent alarms, you can correct 80% of the underlying problems. There is a management information system, capabilities for reporting and trending, computation of statistics in the time and frequency domain. So for instance, you could associate with each reel of paper that is produced a report that gives you, well, the indices, the quality indices, for instance grammage and moisture over the production time of the reel, with statistics as average, standard deviation, and so on. The most modern control systems integrate all levels of control from the process control pyramid that we've seen earlier, from basis layer control to the planning and scheduling level. These systems will also give you remote access and diagnostics, which is interesting if you have just commissioned a production line in a faraway country and you've just come home. You can still interact with the process control system. Some of those systems will even propose tools for control performance monitoring. Each control loop will be evaluated in terms of tracking and disturbance rejection performance using key performance indicators. In this way, you can easily isolate the problematic control loops and you know where to concentrate the tuning effort. Some of these systems will even propose new tuning parameters. The objective of feedback is to cope effectively with change. There are three main sources of change. The first one are disturbances. These disturbances can act at the input, then we speak of a load disturbance, or they can act at the output, and you have here a list of typical disturbances. A second source of change is a set point change, and this is of course initiated by the operator, or we can have, well, a transition between set points, and then we speak of a tracking of a desirable path. A third source of change is a change of operating point, and this source of change is often forgotten. It comes from the non-linearity of the process. If you change operating point, well, you'll have a change in the dynamics. Well, feedback control will also help you to cope with change in the process. Well, the Bode diagram of the loop gain, and this is a reminder from the course of Fundamentals of Control Theory and the course maybe of Digital Control. Well, the Bode diagram of the loop gain is PC, looks something like this. So you have here the crossover frequency, you have a zone where the slope is around minus 20 dBs per decade. Then in the low frequencies you have a high loop gain, probably because you have put an integrator in the controller, and then you have a high roll-off. So this is here the crossover frequency, right? Well, the transfer function from set point to PV is PC over 1 plus PC, and since at the low frequencies you have a high loop gain, well, in those frequencies this transfer function will be approximately 1 because of this high loop gain, and you can see here that variations of P will be mitigated by the feedback principle, right? The transfer function from TV, output disturbance, to PV is 1 over 1 plus PC, and you can see here that in those frequency ranges, right, well, this transfer function will tend to 0, so you'll be attenuating the disturbances dV. And again here, if P is varying, Okay, so if you have changes in the process, this will be mitigated by the fact that you have here a high loop gain, and feedback will again cope with this change in the process. There are essentially three approaches to feedback. The first one is the model-free approach. The control action is based on current and past information and tuning constants, but the process description is never used in the control algorithm itself. A good example of that is, of course, the P&ID controller. It is a fixed control algorithm in which the process description is not used. Of course, what could be done is that you use your knowledge of the process to tune the P&ID controller, but the process description is not used in the control algorithm itself. The second approach is a model-based approach, but the P&ID controller is still used. So you can see those approaches as extensions of the P&ID controller, in the sense that the model is just used to obtain kind of a prediction of the PV that is going to be controlled by the P&ID controller. So you can draw things as follows. You have the PI or P&ID controller. This is the set point, and what enters over here is the prediction, a prediction in the future, and so on, an anticipation, and this anticipation is constructed from a model. Okay, and this model will use MV and it will use PV, right? So you still have a block here with SP coming in, PV coming in, and an MV coming out. It uses a model and a P&ID controller. So in this sense, well, this P&ID controller is kind of a recycle to give you a new controller structure, and this will lead to the Smith predictor and the predictive P&ID controller. Well, in this third approach, only the model is used to obtain the controller outputs, and this is done using static or more often dynamic optimization, and this leads to internal model control that will be tackled in the last section of this course. Another approach which will not be covered in this course is model predictive control. We'll mention it also in this last section of the course. Well, here is some motivation for process control and motivation for this course. I really believe that all engineers should have insights in control, and not only control engineers, and this will allow to take control into the picture as soon as possible. Well, this is a survey of the actual situation, and you will see that there is really room for improvement. Control systems are often delivered without optimization and tuning. Well, the optimization is left for later, but later never comes, and the result is that a minority of control loops are functioning properly. I will show you some surveys that really prove this. Well, the control structures are badly constructed, and this results in, well, badly designed P&IDs and hardly ever updated P&IDs. Control is not taken into consideration during the process design phase. These badly designed control structures come from a lack of classical process control knowledge. Key components, key ingredients of this knowledge are feed-forward, cascade, interlock management, split range, and so on. A systematic approach has to be used to combine these ingredients in order to obtain an adequate control structure. I really hope that this course can help. Control engineers are given very little time to concentrate on optimization and tuning. They have to keep the process running, and when finally given some time, well, there is this fear of the unknown, the fear of causing shutdowns and plant problems. You know that optimization and tuning has to be done on a running machine during production, and it's therefore sometimes difficult to find volunteers for those jobs. I hope that some of you will stand up in the future. I've told you before that most vendors offer control performance monitoring tools. You can use those tools to assess the state of all control loops using key performance indicators. So those tools simplify your job because they simply use simple production data to obtain these key performance indicators. One such tool is TuneVP by Yokogawa, and based on their analysis of control loop problems, they have found that, well, on average 15% of all control loops are in manual. So this is really indicative that there is a problem with this control loop. They have seen that 30% of these control loops have valve related issues. We'll come back to this, and this is probably related to stiction. And that 55%, which is really a huge amount, of loops have encountered oscillatory or poor tuning. Well, here's another publication that shows that various studies indicate that anywhere from 66 to 80% of controllers are not performing as well as they should. For those of you interested in control performance management, this is a nice reference, Control Performance Management in Industrial Automation by Jalali. This is the reference that is used in the course of system identification to discuss the ARIS index, and this course is followed by the control engineer students among you. This book proposes quite a number of surveys that study the control performance of loops in companies, and they give all more or less the same picture. Let us pick one out that studies the situation in North America. As you can see, well, 30% of the loops has control valves in poor condition, 60% has poor loop tuning, 85% has poor loop design, so problems with the control structure, 15% of the controllers are in manual mode, and 30% of the loops are not performing according to the control objectives. With what we have seen before, we can certainly agree on the fact that an abnormal high quantity of control loops are badly tuned or badly designed. This means that the control structure is not adequate. Well, there is a lot of evidence for that, and the indicators that are shown here are very important as they allow you to assess the control performance of a production line. Oscillations are certainly a sign of problems with the associated control loop. It can come from bad tuning, so for instance too much integral action, inadequate use of the derivative action, and so on. Oscillations can also come from interacting loops, so coupling effects, non-linearities in actuators, and a good candidate is stiction. We'll come back to this later in the course, but you have seen that it comes back in these surveys. Aggressive control for processes with a high dead time, and also non-linearities. It could be that around one working point everything is working properly, and then you change working point and suddenly you see oscillations. This is because the process has changed, and what you can do then is, well, use scheduling, as we will see later on in the course. Another sign is, well, alarms that are coming back on the SCADA system, and factory tuning. Factory tuning is, for instance, if you take a P&ID controller from the library, it might be that it comes with those parameters over here. Kc is equal to 1, Ti is equal to 10 seconds, and Td, the derivative action, is equal to 0. We'll see later why this is chosen as factory tuning. But if you see in your faceplate that your controller has this tuning, the original factory tuning, well, there is a big chance that nobody has ever looked at the tuning of that controller, and well, that it is a good candidate to start the tuning exercise. Further evidence is that there is no follow-up on tuning, and this means that the control parameters are hardly ever changed. You will find a lot of controllers in manual mode, and as indicated before, this means that the operator does not have any confidence in the associated control loop, and these controllers and the associated control structure are therefore candidates for an optimization or a review of the control structure. Very often the sampling rate is badly chosen. So for instance, the sampling interval is chosen much too small. There is no filtering or inadequate filtering of PV, which means that the noise that is present on PV might find itself amplified at the output of the controller, resulting in, well, actuator problems. And finally, you'll find lots of controllers that run into the limits MV min and MV max. So either they are saturated most of the time, or the value MV goes from MV min to MV max and back all the time. And this can be the sign that there is a tuning problem or that there is an actuator sizing problem.